there's a lot more this kind of company will try to use microfluid, even some bio means for this kind of rapid detection of COVID-19 virus. So that's something, of course, among this microfluidic, we have also mentioned so that there's additional branch beyond application of these biomedical application also can be used. Microfluidic can be used for this kind of inkjet printing in consumer electronics, and also the actually microfluidic has another important application for, as mentioned, right? Especially electrowetting device can be used for electrowetting based display, also electrowetting based this kind of biomedical, this kind of device, so that seeing one more, I think the key thing here is I mentioned that this microfluidic has been used for a lot more application, right? For this kind of medical diagnosis, pharmaceutical, analytical, drug delivery, and also of course microreaction flow chemistry, industrial, environmental, and plus additional. I should also maybe add one more, right? So even for this additional consumer electronics, it can be also used as mentioned. Why? Consumer electronics, right? Like how can use electrowetting based display, right? Electrowetting based what? This zoom lens, right? Or like a liquid lens. So that this is something I told you is gradually this microfluidic also become quite a lot more application. And one more microfluidic a channel for as most of a cooling. Microfluidic can also use for this semiconductor or electronic cooling. So especially now, I don't know if you know that now if you have a new smartphone, what happened? You have new smartphone, then you have for example iPhone 10. You have about I don't know if you have some idea how many transistors do you have in the smartphone iPhone 10's processor made by Apple. Do you have any idea? That's something would be interesting for you. For typical iPhone 10, how many transistor? In how many transistor in this iPhone 10's processor chip? Any idea? Any idea about this? It's a 7 billion transistor. For new iPhone, I think 12. It can go up to 11 billion transistors. So in this case, you have a lot of transistor in this very small area, so that a lot of heat dissipation. So cooling become more and more important for all this smartphone design. So that's why so that you know that this kind of microfluidic has another important application for cooling of semiconductor chip, cooling of maybe computer or some laptop computer. So I can see this is one of a quite special area, but I do think this should be quite important for real application. Yeah. So that of course we also mentioned about this kind of market, and then so that and again we just quickly show again a highlight so that if we can make this kind of mains device sensor and actuator, so that if you, for example, this particular one we mentioned, right? So it's using some micro bubble actuator to generate, to perturb the flow velocity, so that it can also try to change small microflow, can create some big the kind of microflow change, the flow control, right? So that of course I mentioned microfluidic continue to increase in terms of research, publication, patent, and product. So that become quite important thing, right? So that we also quickly mention about this bubble jet or thermal inkjet. So that what's behind about this principle of this kind of bubble jet inject, thermal inject? We also mentioned last time, right? So basically, this is the key concept of this device. Microfluidic thing actually is a micro heater, and then you apply very like a short period of time of this kind of a voltage. Typically, it's on the order of 10 microseconds, and then so suddenly you will heat up this in near this micro heater, and then what happens? And then so that it can create this kind of phase transition from liquid to vapor. So that that is something is a micro heat transfer, right, with phase change. So this is one of the important thing about this thing, right? So basically, it's of course, it can be complicated, right? So that once you create this kind of phase change, and then this vapor bubble has some unique property. You have increased a large pressure, so that this vapor pressure is much larger. So you can use it as a pump to push this kind of in-outer nozzle. So that that's why this is something is unique in microfluidics. So we leverage this kind of special kind of phenomena in micro scale, right? It's micro heat transfer, micro Bowling heat transfer, and then so create some interesting repeatable micro bubble to use a pump to put in outer nozzle. So this is something I just made sure that this is very unique phenomena, and also the market size is also huge. So that of course globally now there's a lot more people use this kind of inject, right? So that at least I would say at least 14 now. I think this is old data, right? I'm pretty sure this market continue to increase, right? So that and here I quickly show you about those of basic concept again, so that typical, as I mentioned, is you have a micro heater, and then with very short period of time, you heat up the ink and create a vapor bubble, and then the ink will this vapor bubble will push in out of nozzle, right? And then because of hydrodynamic instability, the surface tension of this liquid jet surface tension will fight with inertial force, and then so that in this case, there's some flow instability, then you break the jet into the droplet. So that of course in real product, so that this 1 unit of inkjet is not good enough. What do we need? In real application, in those inkjet printer, what is necessary? We need to have array of this kind of inkjet, right? Unit here, right? So that then we can really quickly to print many this kind of droplet for this high speed printing, right? So that of course once you have array, you not only have 1 or 2, maybe 100,000 of this kind of inkjet unit. Then important thing here, we cannot have 1,000 wire to control this kind of to apply this kind of the voltage to each this kind of micro heater. So in this case, the key thing here is we need also have some special analog ASIC circuit design and a circuit to provide this kind of, I mean, there's additional electron switch integrate with this kind of inkjet print head to do a control of this kind of inkjet, right? So that is one of very important for real product, right? So that of course starting from this HP 550 actually is more than 20, 25 or 30 years old, right? About 50 nozzle. So here I can show you, if you look at under the optical microscopy, so that the typical size is this is 100 microns. So that this is that's why it's a micro, right? This kind of nozzle, right? So that of course there's another branch you mentioned is piezoelectric inkjet. So that they use this kind of special piezoelectric as transducer, right, to provide some special kind of ultrasonic this kind of vibration and gonna some acoustic this kind of energy to the ink, right? And then because some special kind of pressure wave and propagate propagation, and then you will try to like generous droplet, right? So this is different from the previous thermal inkjet, right? And so that, of course, one of the big issue for the inkjet is the piezoelectric inkjet is typically require some fabrication with some special piezoelectric material, right? So that is not compatible with typical semiconductor manufacturing process. Okay, but of course, still there's some company try to make this kind of device, so that again, the key thing here is they have used some special kind of vibration of a piezoelectric, this kind of material, transducer material, right, at certain frequency, so that the certain kind of vibration mode, right, this kind of ultrasonic and spin matter, so it can let this kind of ink, right, to have can eject out of this nozzle through this kind of acoustic wave propagation, right? So that, of course, there's at least several companies like Epson, Tektronix, they really make this kind of unique piezoelectric inkjet product. And of course, Hitachi, a different company, have different product. Of course, one of the important message is so all this kind of micro inkjet, why the key thing here is require to do this kind of integration, right? Not only one, but like in old day 15 nozzle, now it's about 6,000 nozzle, right? So that's requirement, right? Of course, we also mentioned that another branch is Microfluidics II, this kind of bio sensing and medical diagnosis. So that we also mentioned last time. So that the CEFI is one company founded by Dr. Kurt Peterson, who is one of this kind of pioneer in this main field, and he used to work for IBM research for many years, and then he started a series of company, main sensor and also microfluid, is micro PCR thing, and then so that after 911 in United States in New York, so that there's really some problem. Some people work for U.S. Post Office and they die because this kind of terrorists try to send this kind of anthrax spore through this kind of mail. So that's why the government tried to put a lot of money for a new type of homeland security, this kind of technology and product, so that at least Northrop Grumman, but this is, I think this is most like a military, this kind of company to make system for, but you also have some branch work on this kind of interesting system, right, to do automatic this kind of high volume anthrax detection, right? So using this kind of micro PCR, it's okay. So that PCR is one of the important thing to for medical diagnosis. For example, like you probably was asked to do this kind of COVID-19 RT-PCR testing, right? So that that traditional PCR machine in a hospital is very big, like ABI, Applied Biosystem, this kind of machine for COVID-19 RNA testing. So that, but if you make smaller, this kind of PCR, so what happened? And then you can really reduce this kind of thermal time constant. It'd be faster to do the PCR, this kind of process, right? So theoretically, it can be really faster compared with a big machine. So that's why this is one of quite important. Actually, I recently also started a new project to see how can we come with even new idea, not using the micro heater, but also using some kind of new kind of plasmatics way to plasmatic PCR. You can really do the rapid this kind of thermal cycling in about 5 minutes. You can finish the kind of 30 cycle of this kind of PCR reaction in new type of device, right? And anyway, so that we also mentioned this biomass is very broad, right? So that people use micro machine, microfluidics for long list of different applications, DNA sequencing, protein, and a lot more. and so that all this actually is something quite important. Oh, I also mentioned that I actually have some special topic. It's quite about a series of different sequencing technology. But another thing is for protein. Protein is another quite important thing for biomedical area. So that there are different. It's very difficult to do this kind of protein sequencing. So that, but there's some traditional way to do this kind of protein separation, right? So that in recent like 1 or 2 years, so that people in energy, especially United States, they also come with a new type of semiconductor protein sequencing technology. So that you can see all of this kind of microfluid and biomass now they found some unique application in different this kind of field. Of course, eventually in the near future, we would like to do this kind of lab on chip integration, right? So that is something I think last time we also quickly mentioned about this thing. Basically, for microfluid device, once you make smaller and smaller, of course, if a good design, then you can really scale down a lot of this kind of very time consuming, this kind of benchtop process into the, for example, microfluid bowl or microfluid device. So you can really increase a good design. What happened? It can increase sensitivity, right? And then it may also reduce testing time, avoid condensation, and then reduce the sample volume. So there's a series of this kind of way to the advantage how we make this kind of micro machine, this kind of devices or biomass to really get a much better performance, high speed, high throughput, this kind of testing, right, for detection of virus or bacteria, right? So of course, microfluidics has a long list of different kind of material and design use plastic, silicon, metal, glass, and a lot more. Right, so that as mentioned, in general, when we do microfabrication, usually we have two important way to do fabrication. One is called the surface micromachining. It usually is more close to the semiconductor process. Bulk micromachining usually is used etched bar silicon. And so, for example, for surface micromachining, so that basically we have second wafer and then we do some coating, right, on surface layer and then patterning. And then if you can remove this kind of layer and then deposit one more layer, structure layer, in this case, if you can try to release this kind of material, then it become what? Suspended, freestanding structure. So that is one of the quite important things for one the micro machine, right? So of course, another branch is bulk micromachining. Typically, this is used wet chemical like a KOH, ETP, and then this etching depends on the crystal orientation of silicon wafer. So I don't know if you have ever seen silicon wafer. Silicon wafer for fabrication of semiconductor and MEMS typically is a single crystal silicon. I emphasize right here. Silicon wafer for fabrication is a single crystal silicon. What's this? That means this has a crystal orientation, so that it turns out when we do etching of this silicon wafer with a KOH ETP, then we need to be careful about this kind of orientation, right? So that if you use this kind of family of wet chemical, right? But on the other hand, there's another branch of chemical, and then it's isotropic etching. So both have been used in different applications. So again, so that I just quickly show you, of course, another branch is fabrication is we call soft lithography. So sometimes, especially in chemistry, when they do this kind of microfluid device, sometimes they do this kind of micro stamping. That means if you have this kind of wafer on top, you can do some patterning of this structure, right? And then pattern, and this can mold, micro molded. Right, so that is quite important thing we should mention. Like this is a micro molding process. That means from silicon wafer, you do deposition in one layer, and then you do patterning with silicon wave, this kind of a wafer, and then you pour the PDMS. PDMS is kind of special kind of liquid polymer, and then you after a certain time, you put some cooling agent, and then be solidify into from liquid to become a liquid form. Right? So this is a way so that the people try to make us a long list of different kind of microfluid device without very complicated this kind of application process. Of course, this kind of microfluidic device is not new, as I mentioned, so that almost about, you can see, more than 15 years ago, Stephen Craig really come with some new idea. How can we come with this kind of large-scale integration of microfluidic, right? And then the idea is basically if you have some kind of inlet, provide some pressure air or pressurized liquid, and then you can cause some, this can make some space-hard micro pneumatic valve, so that this valve will use as a way to do flow control. But if you have this kind of multiple inlet and flow control, so that in this case you can do very large-scale microfluid integration to perform very complicated function. For example, microfluid multiplexer, right? So that with this kind of X and Y, this kind of multiplexer, you can control the flow in very precise way, right? So that this paper done by Kirpis, no, not Kirpis, is Stephen Craig. They published this one in Science 2002, and then so that they really create interesting this kind of display. You see now, this device is not biomedical, right? It's really interesting to let people understand, so that you try to apply this one for display thing, right? So that that is something, and of course they can also be used to do this kind of large scale, this kind of micro fluidic parallel processing. So that means in this case very complicated. Sometimes for biochemical analysis require do some mixing of different reagent and chemicals, so that in case with this kind of microfluidic, they are able to handle very complicated this kind of biochemical experiment on the chip level, right? So that that is something quite important. Of course, as I mentioned, do you have any question? Any question about a thing? I just quickly go the thing, right? So that another branch is lab on chip. So it's some special branch, right? In this microfluid community, they have concept this idea, or sometimes they call it micro test, micro total analysis system. Basically, is as I mentioned in the beginning, right? So that there's an interesting idea how just we can do the integration of very complicated benchtop process and then do everything gradually on the one chip, right? So that including sample preparation, for example, like COVID-19, this kind of testing, so that the doctor or some medical professional to take sample from you, and what happened? Sample preparation, right? And then sometimes it's concentration of this kind of pathogen virus is too low, and then we may do some filtering extraction, right? Or pre-concentration, right? And then pre-concentration including micro B membrane impactors. Impactors usually work in this air form, right? And then to separation, we can do some CE, capillary electrophoresis, or HPLC mass spec, right? And do some mixing reaction and detection and signal conditions. Basically, we have series of this kind of integration on the chip level, right? So that's something. And of course, among all these kind of microfluid device, there's one important issue is one, your device becomes smaller, and then so that based on fluid mechanics, traditional UG fluid mechanics, so that one is smaller, and what happened? The viscous force will be much more important. Why? The drag force, due to this kind of friction of this kind of especially liquid flow, so that this can create some big issue. So that in microfluid device, basically mixing is much more difficult to be achieved. So that in this case, then we need to think about how to achieve mixing. Right? In big scale, when we have some coffee and put some water and then do some sugar, and then we can do some mixing with some stirrer, right? So that something is, but in micro scale, unfortunately, it's very difficult to generate this kind of complicated turbulence or something. So that in micro scale, it's very difficult. Turbulent mixing is difficult, so that we may need to come with some special kind of microfluid mixer to achieve either the passive or active mixer to enhance, create very complicated flow field to enhance the mixing. So that traditional in a tabletop machine, typically we take a much longer time to do the testing for this medical diagnosis. Why? What's the problem? Because in traditional large-scale machine, so all this biochemical reaction for this separation or detection require the diffusion limit process. So it'll be much slower to do it down. But if you go into much smaller, this kind of microfluid device, and then in this case, basically you can minimize this kind of diffusion time and diffusion length scale, so that it can be faster. So this is one of quite important in terms of if you understand this kind of fundamental, this kind of this fluid mechanics additional, this kind of transport, why of this kind of maybe some concentration of DNA, RNA or something for this biochemical process, so that then we're able to really try to come with much better and faster, from benchtop to what lab microfluidics or lab on chip. So this is another quite important motivation why we make this kind of microfluid device. And of course, in this COVID-19 pandemic, so there's a pressure to see how can we really come with better low-cost microfluid device for detection of virus or DNA or something, right? So of course, microfluid has a long range of different kind of design, right? So that the injection of substrate, more complicated microfluid, this kind of structure, create this kind of vortex generation, split recommendation. So actually, there's a long list of different kind of microfluid device, and then using different design, different dimension, channel width, height, and also velocity, and also RE. What's RE? Reynolds number, right? So that this is something we may want to just read. RE basically is Reynolds number. In fluid mechanics, basically what this is relation, the ratio of two forces, right? It's a low, basically is related to this kind of V L. Okay, so that so basically density, V velocity, and the length scale of this microfluid device divided by mu. Mu is viscosity, right? So basically, it is the ratio of two forces. Why? You have a viscous force, and then divide by this kind of it's the inertial force divided by viscous force, right? So that the Prandtl number is related to what? Packet number. That's related to the this kind of diffusion and convection process. So that for engineer, we do need to understand about this kind of issue, right? So of course, another branch of microfluid device, microcatalytic mixer, so that how can you come with what? Different design of microfluid device, different geometry, create complicated chaotic flow in this thing, so that then you can achieve some much complicated flow field and have a better mixing result, right? So that of course one of quite unique this kind of microchaotic mixer is done by this kind of special group in, I think, in Harvard University, George YK. So basically they want to come with this kind of microchannel, right, with some special patterned service channel wall. And if the velocity with some special critical velocity field, and then you can induce some secondary flow. And then this can create some vortex if your velocity is high enough. So this is one of a quite unique way to create the kind of microchaotic mixer. Okay, I actually, about 20 years ago, I do have some research in this area, right? So that and this paper they just mentioned by this George YK, right? So that they mentioned about you can possibly you can complicate the flow field, but actually they don't really show why this kind of flow velocity field can create chaotic dynamics thing. So that 20 years ago, actually, I tried to create some model, okay, to for microchaotic mixer and the simulation experiment. I demonstrate this kind of chaotic the existing of chaos in microchaotic mixer. So I just mentioned so that this actually turned out to be non-trivial. So the key thing, this keyword is, that means they try to create some very complicated two-dimensional or three-dimensional flow field in microfluidic device. 2D or 3D, this kind of complicated microfluidic device channel, so that in this case you can create very complicated flow field, right? To, in this case, what, to enhance this kind of mixing, right? And then so that and so in case it can be much quickly to do the mixing in very short period of time and the size space, right? So this is one of impossible, because to be able to do this kind of analysis simulation require you have a good understanding about mechanics, right? Like fluid mechanics, also nonlinear dynamic system, and then you're able to do this kind of analysis simulation to understand this kind of chaotic behavior of a microfluid mixer. Okay, as I told you, I do spend some time to generate this series of this kind of chaotic mixer research about 20 years ago, right? So that I said, this is something is non-trivial to do, but once you have good design, then it can be useful, right? And of course, beyond this kind of microfluid device, micromixer, so that another important thing is sometimes you want what? You want to process large amount of the fluid for chemical engineering, so that so this is something once you have a microfluidic reactors, so that you have a good design, it may have increased heat transfer. Right? Of course, if another extremes, if a good designs micro reactor thing, you may have enhanced some mass transfer. So that these two are quite important in practical engineering, right? So that of course, as I mentioned, one of last time we mentioned like this, if you this company, chemical engineering company in Xi'an, China, they try to use this kind of INMs, the microstructure reactor, and then to do this kind of chemical reaction, right? And make this kind, generate this kind of nitroglycerin about 10 kilogram per hour, right? So that to increase this kind of efficiency to do this kind of production of nitroglycerin is some of the special drug treats some cardiovascular disease, right? So the key thing here is this why this can work. Huh? Why this kind of thing can work? I want to say why why we use this kind of microstructure reactor? Huh? Any idea? As I mentioned, right, so that once you have microstructure, this kind of reactor, so that in this case, the fluid, right? If this some chemical have try to create some very complicated flow field, right, and then increase this kind of mixing, right? Also increase this kind of heat transfer a lot. So that in the case, that is one important thing, right? In the case, you increase large surface volume ratio, right? So this is quite important, for real application. And then, as I mentioned here in previous slide, yeah, for this kind of chemical engineering process, we want to have a good heat transfer and also good mass transfer, so that in this case, this microstructure reactor basically is really trying to create a large surface to volume ratio, so that it can really do the kind of chemical reaction engineering in much more efficient way. And then so that is, and order make it much more efficient, right? So that is something quite important. Okay, I don't know, do you have any question? No question? And then of course, we just quickly show you another branch of microfluidics is again microelectrophoresis, right? Or some nano. So that last time we quickly mentioned, so that there's 4 phenomena in this electrokinetic behavior, right? Electroosmosis, electrophoresis, and then the reverse process of this one is like streaming potential. And then electrophoresis is basically is what? Electrically we do phoresis separation, right? So this electrically I create some osmotic force, right? And so this usually used as a micro pumping, right? This is a separation of this kind of mixture of DNA, mixture of different microparticle, right? On the other hand, sedimentation potential is reverse process, right? Once you have some microparticle or maybe DNA or something, and then once you move, and then you can generate some electrical output, so that this is a reverse phenomena. And of course, we also mentioned, like if you look at more detail about how we can generate this kind of electroosmotic flow in microchannel. So key thing here is we need to have some special kind of a microfluid channel. Sometimes they call it flow cell. So that the key thing here is we need a microchannel. Okay, and then but this microchannel is we make sure that the surface of this microchannel wall as what? Most likely, no, it's related to dielectric material. So when and then once it put this kind of ionic solution, like for example DNA solution. So DNA is what? It's net charge, so some ion in this kind of solution. And then in this case, once you have a dielectric this material, so that they have generate some charge, and then your ionic solution like DNA solution, protein or cell, so then they have a form this kind of electro double layer. So this is something quite important. Once applied, once they form this kind of electro double layer, and what happened? This is called electro double layer. And then in this case, once applied this thing, we can try to find those kind of ion, mobile ion, which can move around in the direction of electric field. That's quite important thing. you mentioned so that we have certain kind of electric field. Once apply some voltage, so that in this case, if the channel is not large, it's channel very small. It is channel size. It is channel size like 1 meter. What happens? And if it's very big, and then in this case, it's very difficult to. That means to generate this kind of velocity field to because there's some viscous drag force, right? Once you move this kind of ion, maybe you different color. This mobile ion will move in one direction based on F equals QE, Coulomb force. So that you move and then, so once charge move around and then in certain direction, so there's a viscous force will try to play important role, right? To bring some additional liquid next to this mobile ion, so that if the channel, this size is very small, if there is very small microchannel, so that in case you have this kind of way to now use viscous drag force to bring all the liquid in one direction, right? So that is one of quite important concepts. So basically, how we can create electromotive force. Basically, you have certain charge. Most likely, it's dielectric material at the interface, eternal velocity of electric field, right? So you apply this kind of voltage, and then you're going to generate this kind of thing, right? Electric field multiplied by zeta is zero potential, epsilon with permittivity, and mu is about velocity. So mu is viscosity. And of course, we can manipulate electric double layer by different concentration of DNA solution, ionic concentration. Right. So last time we were mentioning about this electrophoresis chip, right? Core chip basically is a horizontal channel is for what electrophoresis. Vertical one is for the kind of a metering, right? You try to with some electro-osmotic flow, so that you try to inject certain kind of fluid, right? You want to do this kind of separation, right? Then so that in this case, this kind of microfluid device, microelectrophoresis device can be used for separation of analysis of DNA mixture, right? For example, there's 100 base pair, double-strand DNA ladder, okay? And of course, the key thing here is when we look at this kind of microchannel for this kind of separation, DNA separation of microelectrophoresis, what's the key thing? I mentioned so that depends on size, okay? So that if your microchannel is much smaller, your microchannel diameter is very smaller, and then so in this case, you may think about you actually can really let much more efficient do this kind of DNA separation. Okay, so that is quite important thing. No, so that actually if you look at this paper, they also demonstrate, right? So that microfluid channel can create much better performance for separation of DNA on separation. I don't. Do you have any question up to now? Any question? And of course, this kind of electrophoresis device is not only useful for DNA or other thing, right? It can be also used for wine separation analysis of wine, right? You know, wine or liquor is what? Also mixture of different small molecule, right? So that in this case, this paper published almost 20 years ago, they demonstrate it's possible you can come with multi-enzyme assay to do this kind of a wine chip, right? So of course, last time we also mentioned what's this? Basically, is another branch of a microfluid device using electrokinetic, right? Made by Caliber Life Science. So basically, they demonstrate if you I think most of these microfluidic device made by glass, so that and then you have an inlay, and then you have some micro channel, and then in this case you have a good design, so that you let those kind of DNA to go through this kind of micro channel, right? And then plus additional electrophoresis, right? So that basically this is one of pioneer, right? Caliper is the first company who really turned it a real product in terms of this electrokinetic device. And then I think eventually they went to the IPO in New York stock market. So that, of course, as I mentioned last time, we have a goal for this kind of microfluidic device, microfluidic system, or lab on chip. What do we want? What do we want? What do we want for this microfluidic device system? What do we want? We hope, as a user, right? We hope we can really quickly do this kind of microfluid process to maybe COVID-19 testing. Why at this moment still, why this COVID-19 pandemic really create a big trouble. Many people have to do this kind of COVID-19 RT-PCR testing, or even this kind of antibody testing, right? So that, but main traditional way is very time consuming. So that can we really think about using microfluidic device can do this kind of cell lysing, PCR, and electrophoresis, right? So that that is possible. Of course, at this moment, from the semiconductor industry, so they also have some way to do this kind of 3D-dimensional integration of multiple this kind of IC sensor microfluidics. So that in this case, if you can really do this kind of integration on one wafer with multiple this kind of step for example, cell lysing. What's the cell lysing? Basically, we try to kill the cell and extract this kind of DNA, RNA from the cell, right? And then if the concentration of this kind of DNA, RNA is so small, then we need to do amplification of this kind of PCR. And then finally, once you amplification, we also think about some electrophoresis, right? So this is something just mentioned that you can see in 1998, people already have this idea, but unfortunately, see, it really take time to make this kind of integration. So it's still non-trivial from my point of view. Okay, so that this idea is gradually, I would say, become the real product. And I think I will show you recent product launched by this IMAC in Belgium, work with Johns Hopkins University. They do really do this kind of integration and make a real product now. So that I told you all this research, right, from a prototype, you demonstrate this kind of concept micro in the lab, and then gradually become the product. Oh, it really take time, take effort, but gradually, finally, I just say this in the industry, people gradually try to make this kind of more realistic kind of a system and product. So I can see it's non-trivial, but at least this something now we gradually see some company really try to do this kind of integration, right? Not just one specific this kind of device for two things. Let me quickly show you one company. So this company really try to demonstrate a real product. Let me show you this.
The ambition of My Diagnostics is to globally shift the way individuals and communities manage their healthcare. My Diagnostics offers single-use disposable diagnostic tests built around silicon chip technology in a test card with preloaded reagents. At the core of the test card is a microfabricated silicon chip called the nanofluidic processor that processes liquid clinical samples using capillary forces alone. The complete blood count test shown here only requires a few drops of capillary blood. Other tests require a swab or any other easily accessible sample. The test card is inserted into a reader for testing to begin. Next, capillary forces draw the sample in the test card towards the nanofluidic processor, built out of 2 layers of silicon, allowing the blood to be distributed throughout a network of precisely engineered microchannels. The innovative design of the chip includes valves that purely function on capillary forces. These unique valves enable the sample to be temporarily held in a channel and measured to a specific volume with nanoliter precision, while any excess is siphoned off into a waste channel. Various microchannel configurations are possible, offering great versatility in the design of nanofluidic processes that automate virtually any diagnostic workflow. When the test card was inserted into the reader, reagents were released and drawn into the nanofluidic processor. Once the reagent interacts with the sample, the valves are opened, allowing the capillary forces to pull the sample mixture forward. For CBC testing, 2 reagents are used. The first dilutes the red blood cells to make them easier to count and to reveal the platelets. The second reagent lyses the red blood cells. Their cell membranes are broken down, thereby making white blood cells more visible. This lysis process is completed in a timing channel, allowing sufficient time for the lysis reaction to take place. This NFP has 2 outlets, one for white blood cells and one for the red blood cells and platelets. Both enter into the test card, pass through the detection or flow chambers, and make connection with capillary pumps that provide a pulling force. For its CBC test, My Diagnostics uses lens-free imaging, a novel technology that only needs a light source, image sensor, and flow chamber. The cells diffract the light that's emitted by the light source, creating holographic images that are reconstructed to allow machine learning techniques to classify different blood cells. The potential applications of blood cell analysis are very diverse. Imagine how easy it would be for a physician or a healthcare worker to perform tests on the spot, or for a chemotherapy patient to monitor their blood count from the comfort of their home. My Diagnostics takes a giant leap forward in high-quality, efficient medical decision-making. Lab-quality diagnostics for everyone, anywhere, anytime.
Well, so this is, as I mentioned in our lecture note, so that the one I show you in lecture is a research paper, right? Demonstrate this idea about this integration, right? It's almost more than 20 years ago, but I say finally you can see this company. I think this company is from the technology from the IMAC in Belgium. IMAC is one of top the semiconductor research lab in the world, and then work with Johns Hopkins, so that really make interesting this kind of silicon-based microfluid device to this kind of lab on chip, and then they try to demonstrate this kind of system. Of course, one using also additional optical detection without any lens, so that they're able to they show a possible to use COVID-19 testing and a series of other applications. So that I told you this is something from basic concept to real this kind of thing. It really take a long time, but at least I would say this give you some idea, right? So from the proof of concept device for this kind of microfluid device to make a real product, it still take time, but that is something finally can shoot, right? So that of course I already show you about this in the research field. Many people try with many different kind of device design, right? For DNA separation, DNA analysis, so that that's something. Of course, like almost 15 years ago, I also have actually this device made by my peer student about more than 15 years ago. So that basically is a silicon glass microfluid device with some micron pillar structure, and then they do another bonding. Another bonding is quite spatial bonding technology. Try to bond the silicon to glass, right? And then so that and again, so in this micro channel, we have this kind of some micron silicon pillar array, so that this is used deep RE, deep ready ion etching, and then try to do like a dual photolithography, basically do some projection lithography and contact lithography, so that that is something we demonstrate this kind of very high aspect ratio of application. The diameter of this silicon is 0.3 micron. The aspect ratio can be 51. So that so this is something almost more than 15 years ago when I worked with my peer student, and then so that really achieved some excellent performance 15 years ago. Okay, and of course, the deep RE has been widely used. Now, do you know how we use this one? I don't know if you have in the other lecture you mentioned about this deep RE. It's one of the important microfabrication process. It's deep reactive ion etching. Okay, so that before, you can see more than 20 years ago, people use deep RE mostly make a micro machine or microfluidic device. But now the deep RE have been used in those kind of 3D IC integration, also used in your smartphones, those kind of main sensor. So that so this is something I should let you know, that deep RE gradually become one of a quite important technology in semiconductor industry. Why? For saying why, if you look at the recent presentation by TSMC, right? It's #1 semiconductor manufacturing company in the world in Taiwan. So that what do you think? Actually, they really demonstrate this kind of very unique TSV through silicon via, why for semiconductor integration, so that the deep RE has another, not only make a microchannel, some pillar, also a TSV through silicon via. Why? So in this case, it's an important technology for 3D integration. Your smartphone, like iPhone, new iPhone, most likely it's made by the TSMC in Taiwan, so that do this kind of integration on not only semiconductor IC chip, but also the other device. Do you understand? So that this become more and more sophisticated for this 3D IC integration. I can imagine, so microfluidic device is in the stage for integration, right? In this kind of, in the most advanced semiconductor foundry. I don't know, do you have an idea about this company? TSMC, of course, in Taiwan, of course, I know sometimes people will, some American will mess up between this Taiwan and Thailand, but TSMC is one of become the #1 semiconductor foundry. If we can really make 5 nanometer, this transistor for Apple's, this kind of smartphone IC chip, and even better than Intel technology, better than Samsung. So that this is something quite special, right? Because I originally from Taiwan, so I do have a series of a friend who work for TSMC for this thing. So we see this kind of technology, micro and nano fabrication technology become better and better, right? So that by next year, they are going to have 3 nanometer, this kind of semiconductor technology in mass production. So it's quite amazing to see this kind of micro and nano fabrication gradually going to this kind of small scale for this kind of semiconductor. Okay, so here I show you, so that at least 15 years ago, I work with my student really come with a unique this kind of a micro channel with the micropeeler, and then we demonstrate this kind of unique way to do this kind of DNA electrophoresis, right, for larger molecule without this kind of CB matrix. Traditional electrophoresis, what do we need? We need some special kind of CB matrix, some gel, right? So that in this case, we can do separation of DNA based on electrophoretic mobility, right? Charge mass ratio. So that typically for this kind of separation of DNA or molecule, right? So depends on what? Depends on electrophoretic mobility of this kind of bio molecules, right? So that is something is important for you to understand, right? So that of course basically it relates to the charge, maybe Q and mass M ratio. Q in charge. Typically DNA is 1. I don't know if I think you are in the biomedical engineering, right? In terms of charge, what kind of charge DNA has? Huh? You are in the biomedical engineering? So I don't know. For DNA, what kind of charge do you usually have? Molecules? I think maybe I should also have some question for you. What kind of a charge? Any idea? Typically, DNA is a negative charge, right? But different size DNA, so that then this kind of charge mass ratio is different. So that's why when we do the separation of the electrophoresis separation, so that the key thing here is what DNA separation is really based on this the charge mass ratio, right? So that the large DNA molecule has a different charge mass ratio compared with small DNA molecule. So in this case, once you have this kind of micro channel or glass capillary, so that we apply the voltage, and then we're able to different velocity of this large DNA, small DNA, they have different velocity, so that in this case we can do separation. Do you understand? So that I just tell you know this is quite important, I think, for biotechnology. Okay, student, you need to understand. Basically, we have sometimes we use this mu. Why? Mu is this kind of electrophoretic mobility. So if you apply the voltage, then what will happen? So basically, we have apply the voltage, and then we generate electric field. Right? So that based on F is QE, F Lorentz force, Q charge, and electric field, so that we can calculate, right, this kind of efficient charge, so that we are able to look at this kind of way to study this kind of electro dynamics of DNA in applied field, right? So that in this case we're able to do this kind of understand this kind of dynamic behavior of this kind of mixture of DNA, right? So of course that is one important thing, right, for us to understand how to think. Right? Of course, I show you that when I 15 years ago, I made this kind of microchannel with some micropeeler array. The goal is what? Our goal is the micropeeler array want to replace the CV matrix, so make a more simple design. Do you understand? So that if you have CV matrix, that means you put some special polymer in microchannel, is much more complicated. And right, so that's why at that time we just demonstrate possible. We can really try to come with this simple microfluid device with some micropeeler array without CV matrix, and then do this is demonstrated. We can do this kind of separation of at least 2 big DNA molecules, T4 DNA and lambda DNA, right? So do you know how large? Lambda DNA is a 48 kilobase pair. T4 DNA is like 100 base pair. It's very large DNA molecule, long chain DNA molecule. So we demonstrate with this kind of microfluidic channel with some micrometer array, we can do separation around, I think, 100 or 1 second. Okay. Of course, let me show you this video again. So basically, it's vertically, we apply voltage for electro-osmotic pumping, and then to do a separation of mixed DNA in this kind of microcomputer array. Okay, so this just gave you some demonstration, right? So this kind of a micro or nano or some micron, this kind of microfluidic device can be useful for this kind of electrophoresis, okay? And of course, we also show that it can also use to do separation of a smaller DNA molecule. This is some special enzyme digest this kind of lambda DNA. And then, of course, last time we also mentioned another branch, right? Surface tension based microfluidic device basically is once your size of the channel becomes so small, less than 1 millimeter, so that in this case, you can, especially this is critical size. This is about 1 millimeter. So it's smaller than its weight. The force or body force weight, right? F equals the mg force will be much smaller compared to surface force, surface tension surface force. So that this is something that means for those microfluidic device smaller than 1 millimeter, so the surface tension becomes much more important. Okay, so that in this case we are able to demonstrate to show how we can manipulate this kind of surface force, right? So that of course. Last time we quickly mentioned. So electrowetting basically is we have some liquid droplet, and then we have at least apply some voltage, right? So if electrically we can really apply voltage, we can change surface tension, right? Without voltage applied, so that surface tension can change. Then we can adjust this kind of contact angle. So this is one quite important. Of course, in order to make a more practical design of this thing, so if you drop it on this metal electrode, and what happened? It turns out it's more difficult to control. So that's why in this case, for more practical design of this device, we have to use electrowetting on dielectric thing, right? So that in this case, electrowetting on dielectric is more practical, so that we are able to do the manipulation of droplet by apply the voltage. So that you can see the key thing here is we apply the voltage between this droplet and this additional this electrode, but in between the droplet and this electrode, we have some dielectric material. So that in this case, we are able, especially to look at engineering about this kind of surface force, hydrophobicity. So that's something is quite important. So that doing that, so that in this case we are able to, if you want some dielectric layer like silicon dioxide or some maybe Teflon or other some material with different dielectric constant, so that in this case we are able to engineering this surface the contact angle and hydrophobicity. So once you do this thing, then in this case you see we look at interfacial tension. interfacial tension actually have a different meaning, right? So that the case in here, we look at those kind of gamma solid to liquid interfacial tension that relate to this kind of surface tension. But there's additional interfacial tension between liquid and gas or solid and gas, right? So that in general, basically, for this electric wetting, basically is the surface tension gamma is equals constant and then modulate by this term, voltage dependent term, right? So that and then the counter angle is also depends on this kind of voltage, right? So that is something, of course, in practical thing, we need to do this manipulation. If you look at counter angle as function of this V voltage applied, V squared, then what's the problem? V squared means that the sign of this kind of voltage applied have no role. No, they will not change this kind of actuation. So that in this case, for engineer, we need to what? For engineer, we need to do things. If you apply some bias voltage, V, that means if you apply that means I have a 2, right? That means you have another V DC and plus V AC, right? So that in this case, we are able to manipulate this kind of thing. Do you understand? So that this is what we call the bias voltage. And AC, this is larger than this VAC4. Right? In this case, we can try to think about this kind of small perturbation through the AC thing, right? So that in the case, we can do some control about this direction. So that it become one of quite important thing we try to show. Let me put down a little more detail. Basically, is V. That means here we have C, and then we have a VDC and VAC, and then additional parameter maybe K square. So that if the VDC is much bigger than VAC, so in this case we can simply show why. So that the big number Y and then 2 VDC VAC and plus AC square. Okay. So if VDC must be a VAC, so that in this case, VAC small number square, this so we can here. Why? So this is constant. So in this case, eventually we show this kind of counter angle will be, you can linearize actually, linearly proportional to this VAC, apply AC voltage apply. So that in this case, I can really try to do this kind of way, why? To manipulate this counter angle, and then so that that is one of very important thing, right, for practical engineering. So that of course, again, there did at least 2 different design open EWA device, right? So that basically is the only one side you have this kind of dielectric material on this kind of counter electrode, and then we have additional wire to can here. So and then of course we have additional hydrophobic coating, right, to make sure that we have a reasonably good this kind is term the counter angle, which when there's no applied voltage, right? So that and this is something we can really do this thing. Of course, there's another branch is if a 2 layer, right, 2 side will have a closed electric wetting device, so that in this case, basically both sides we have this kind of electrode, right? So that basically we're structure or pattern this kind of electrode on the bottom side, and structure not on the top side. Do you understand? So this is something. In this case, we can try to make some more sophisticated design, right? And then so that's something is quite important. So of course, in this case, you can see we can really try to apply. We have a multiple this input to control this kind of voltage for this kind of multiple electrode, so that to manipulate this droplet to move around. So that is something quite important. Why? If you want to use this electrowetting for practical biomedical analysis about sample, biological sample for COVID-19, for cell suspension of blood, so that you need to have way to manipulate the droplet for different things, right? For example, do the mixing and splitting and additional processing. This is electrowetting based microfluidic device. So that, of course, last time we mentioned that it's possible this kind of electrowetting device can be used not only for liquid droplet, but also try to handle those kind of virus suspended in the air, or bacteria suspended in the air, right? Bioaerosol. So that this is a possible idea, because handheld airborne bioparticle device. So that the key thing here is once a good thing, then you can use for anthrax, SARS, or TB, or COVID-19. So here I just show you last time. Basically is basically consider of two important technology, right? Basically, you need to have some micro filter to filter this kind of virus suspended in the air or bacteria suspended in the air. And then once you filter, and then how you use the kind of droplet, electrowetting based droplet to sample those kind of capture those kind of pathogen, the virus, bacteria. So that is something. Basically, you may have some micro filters, and then you have additional this kind of a droplet controlled by voltage, electrowetting based droplet. Right? This was done by Professor SK Cho. Actually, I know Professor Cho when he was in UCLA many years ago. So that and again, so this device they really show this kind of idea in almost 13 years ago, and demonstrate it can possible. You can make this kind of device. Why for this thing? Unfortunately, actually, about 2 or 3 years ago, I talked to Professor Cho, and unfortunately, he really didn't make a real product. Why? If this it can really make things, maybe it can useful for COVID-19 this application. Of course, on the other hand, there's one company, GenMark, in I think near San Diego in California, United States. They really try to push very hard to use electrowetting microfluidic integrate with electrochemical sensor and make a product, so that it's one of a real product, and they got this kind of US FDA approval several years ago, so that they demonstrate they can file this FDA 510K. They can really try to do this kind of testing for different kind of virus, right, for real application. Right, so that the key thing here is from basic research to really make a proof of concept device to make a product, it still take time. So that at least this particular GenMark, right, they really make this kind of special kind of integrate the microfluidic cartridge, so that in this case they have electrowetting, and also they have some additional PCB board with electrochemical sensor for this kind of integration. Okay, and of course we also mentioned that the electrowetting also used for electrowetting display. So key idea is once a droplet you want to display, basically you need to have some droplet with some color, right? Maybe some fluorescent dye molecules. So then in this case, you can see this liquid Vista is a team from Philips Research Lab in Europe. Why? So that they have an interesting idea of this kind of three electrowetting device. Each device they have different color droplet, right? So that in this case, if I manipulate the location of this droplet for 3 droplet, then you are doing some mixing and let the light pass through. So you can really try to create this kind of different color, right? Of course, as I mentioned, another branch is electrowetting is a microfluidic for zoom lens, right? So very optics, is actually one company. Basically, they try to use the voltage to manipulate the droplet for at the zoom length, adjust focal length, right? So that again, this can be useful, right? So that of course, as I mentioned, that several years ago, this French company they make a prototype, and eventually we see that Samsung in Korea and Xiaomi in China, they really try to push this kind of electrowetting as a liquid lens for the real smartphone, right? So that that's something that is. So they claim this is one of I think quite important matter between the basic research by manufacturing to real consumer electronics, so that I can see this electrowetting device has a potential for this consumer electronics. Of course, there's a continued great increase of this kind of propagation and pattern in this electrowetting. So that I don't know, do you have any question? I'm sorry that we have a limited time, but any question for this electrowetting microfluidic? Again, any question about this electrowetting microfluidic? Huh? No question? Okay, so that if not, then I still need to continue. So that basically, we just try to mention this another branch of this kind of device. Actually, this is device also quite important, right? For a microfluidic, this kind of mass spectroscopy, right? So that the idea is traditional mass spectroscopy is most likely do some maybe separation or analysis of some protein or something biomolecule. So basically, you use some special kind of high voltage and then do some electrospray ionization. I mean, you let those kind of your sample go through this kind of particle filter and then has some high voltage to analyze this kind of sample, right? And then in this kind of vacuum condition for mass spectroscopy chamber, they try to do this kind of separation, right? They look at this kind of spectrum, so that this is one of a very unique technology. Exists for a long time, but how we can come from traditional this kind of mass spec to micro, why micro this main micro machine based this kind of electric spray now for the thing, right? So that again they demonstrate, right? So once you basically the key thing here is once you have spatial micro nozzle, we let this kind of apply some voltage to generate this kind of unique this kind of electro hydrodynamics to ionize this kind of most like a bio molecules, right, to do ionization. So that in case they demonstrate this work I think done by Professor Yusheng at Caltech, right? So that they demonstrate basically it's possible they can do this kind of separation of protein or major protein. Okay, so that's something quite important, right? So that of course, and then they demonstrate the key thing here is usually you need some special voltage to induce this kind of electro spray ionization. But of course, if you have micro channel, a micro nozzle, most likely you can maybe use smaller amount of the voltage to induce this kind of telecom for electro spray ionization, right? So okay, so that's something important. And along this kind of mass or micro machine based mass spec, actually they do some company try to really make a product, especially like Professor Richard Sim in in London have been working on micro machine mass spec for a long time. I know he has a company really try to make this kind of conversation about this kind of microfluidic device as a product, so that I just show you about, for example, give you this kind of reference for you to think about this thing. Right? I know he has a company to really try to commercialize this kind of main space micro mass spec, right? Because why this is important? Typical this mass spec have been used in the research, in drug research, medical research, but each mass spectroscopy, this machine is super expensive, at least $1 million. So that if you make a smaller micro machine, essentially it can become low cost, right? So that's the motivation. People want to make a low cost, this kind of mass spec, right, using micro machine. Okay. So anyway, so that we also run out of times. Of course, another branch of this kind of microfluidic is using inertial force. According our mechanics, engineering, of course, inertial force is important, right? So lab on CD is another interesting idea, so that once you make a microchannel in this CD or DVD, and then using the kind of micromotor to spin at different speed, different angular velocity, and then you inertial force and push this kind of liquid sample to do this kind of flow, microfluidic flow, and sometimes you can do some separation analysis, so that this is something quite important, right? So of course, there's Professor Mark Nadeau in UC Irvine have been working on that on CD for a long time, so that he actually has a technology license to Samsung in Korea for this kind of lab on CD, this kind of product, right? So of course, I think we almost run out of time. So anyway, so that there's a long list of different technology in microfluidics. We briefly mentioned about traditional microchannel, right? Glass microchannel, or droplet based, electrowetting based, right? And also the electrokinetic microfluidics. So lab on CD is another branch of inertial based microfluidic, right? So that and gradually people really think, right? Of course, there's another important area for microfluidic or biomass is for this kind of sequencing, right? This kind of DNA sequencing have been very important in biomedical area, right? So that basically engineer will look at what's DNA. DNA from our basic engineering point of view, basically it consists of ATCG of different kind of biomarker, and then it's long chain biomolecules, right? So that how can we do this kind of DNA sequencing? Traditional way, of course, basically our goal is clear. How can we do the complete sequencing of this kind of DNA molecules, right? To get all the ATCG. But casing here, traditional way is very time consuming, right? So that of course there's a series of technology, conventional way, Sanger style, and then 454, Illumina, and then helical, and then PacBio, 3 surgery. There's a long list of different technology people continue to develop one thing, right? So again, the key thing here is in the recent year, micro and nano technology gradually used to make a new generation of this kind of sequencing device thing, right? So that from traditional thing, right, 20, 30 years ago, it's very challenging, very expensive, but gradually now, so that's why people actually make interesting products. So there's also some similar to semiconductor industry, there's Moore's law in this kind of DNA sequencing. So in the past more than 20 years, the cost of DNA sequencing reduced dramatically, exponentially. So this implies so that there's a lot of new technology we use in this area. Okay, I think we're almost run out of time. So do you have any question for today's lecture? Any question? So that if not, I think at least any question? Any question? I saw that you're very quiet. Huh? Any question? If not, then probably I think that's it for today's lecture. But again, so if a question, feel free to ask, right? So I do understand it's important, right? So that if you don't ask question, there are two things. One thing you understand everything. Another thing you maybe you didn't really look at our content to ask questions. So again, so that I think do think this microfluidics become very, very important in the coming this kind of year, especially COVID-19. So that hopefully you can learn something interesting. Okay, so I think that's it for today's lecture. So if any question, please feel free to ask through the maybe Professor Weibo, their thing, and then so. Okay, I think that's it for today's lecture. Okay, bye bye.